Same thing for absolute encoders. What's an incremental and an absolute encoder, and what's the theory behind how an absolute encoder works and those electrical signals appear. Then we're going to talk about typical mechanical packages. How do these things come? How do you use them? Encoders are round and they spin, but you can use them to measure lots of different types of motion, speed, and position. So how do those packages look? Then application considerations. You're designing a new product. You need to use an encoder in it. What are some features of encoders that you should consider? Maybe even not consider an encoder, maybe other types of feedback. What are some of those considerations to consider when you're choosing that? Then the last thing we're going to go over is application examples. So basically, you know, when I look through, and of course I make sure I have my NDA, I snap pictures of where our encoders and other feedback devices are applied throughout various industries to give you an idea of how they're utilized. So the first section we're going to go over is the basic principles. What are encoders used to measure? Velocity, position, distance, angle, flow. You probably wouldn't expect some of these, especially angle and flow, but they're used for a variety of things. So how fast is something going? What's the position? A train, I love the train example. I get involved in a lot of train applications, and we get encoders installed on the drive wheels of trains, not only for measuring the speed of that train on the wheel, but also the position. Maybe you're X-ray scanning railroad track, and you need to get a unique position along that track for if you find a crack in the track that needs to be repaired. So velocity, position, total distance, a linear distance maybe. Think of an XY table on a CNC machine or a print head on a large inkjet printer. You need to know the total distance that it's gone. Cut to length applications, you're measuring footage of pipe. You just need to know the distance you've gone in one direction. Angle is another common one that you need. Our encoders can be used to measure the angle within a circle. Maybe it's the deflection angle of a cable coming out of a crane. We'll go into a few of those in our application examples later. And flow, you can put encoders on baffles that rotate. You can measure the flow and estimate the volume of a product with an encoder. So what do they look like? How do they work to do this? Encoders have been around since the 1950s. Our company has been around since 1969, so we had our 50th anniversary last year. They've been around a while, and the technology actually hasn't changed that much. It's improved, but the theory hasn't changed. How they work is you have an LED. Used to be a light bulb. Now it's an LED on the base of the encoder shining light through a code disk. And on this code disk, you have little lines. And these lines interrupt the light going through the disk. So when you hear of an encoder there's a resolution, that resolution is equal to the lines on the disk. If somebody says, oh, I have an encoder and it puts out 1,000 pulses per revolution, it's because there's 1,000 lines on this disk. And as every line goes by, the light interrupts it. Now that interrupted light is received by a photodetector right here. So the light goes through, it starts pulsing by being interrupted by these lines, and those pulses are received by a photodetector assembly. That creates a sinusoidal voltage. That sinusoidal voltage is then put through a variety, depending on the manufacturer, of different board designs. But all these boards do in an incremental encoder is they take that sinusoidal wave and they make it square. And that's when you end up with square pulses that you'll run into commonly in the field. So if I have 1,000 lines on this disk with the light shining through, my end result is I will have 1,000 square pulses per revolution of this encoder coming out of this top board. This is a picture of an ASIC, a photodetector assembly. That's where all the magic happens, receiving that light. There's other ways to skin the cat, as they say, with this. Magnetic, capacitive, inductive, and analog are all other methods to accomplish this. The majority of encoders that you will run into out in the field are optical. The majority of our encoders are optical, and many of our competitors are optical. The reason being is optical is still the most accurate way to go with a rotary encoder. This is a picture of a magnetic encoder. It has a small neodymium magnet here. It's two-pole. If you were to draw a line here in the center, you have a north side and a south side, and it's up inside of this. There's some fancy Hall effect sensors that detect the changing in the magnetic field, and rinse, repeat. At the end of the day, it takes a sinusoidal waveform created by that spinning magnet, it squares it, and it makes square waves. So when you buy other encoders, if you're looking at different types of technology for your encoders, they all output the same thing, whether it be magnetic or optical, capacitive, inductive, analog. They're going to put out square wave out the end. It's just how did they accomplish getting that sinusoidal wave formed. They all have their different advantages. Capacitive and inductive are relatively new technologies. We actually don't have these two, but they are out there, and they're very useful in the low-cost market where you do not need a lot of accuracy. Magnetic is very rugged. You don't have a glass disc that can break, but again, not as accurate as optical. Common waveforms you'll see coming out of an encoder. This is what I was talking about, a sinusoidal wave that'll be generated on a photodetector assembly as the light gets brighter and darker from that code disk interrupting the light. And then our encoders, all of our optical encoders, take this sinusoidal wave and they make it into a square wave. So it'll look like this coming out of the wires on that encoder. Now, there are some manufacturers out there that don't square their waves. We're not one of them, but they do exist. And you'll see encoders that say sine, cosine, or 1 volt peak to peak, and they're actually just outputting this sine wave raw. And there's a variety of reasons. We won't get into the 101 of why you may want to do that, but that is out there in the field. So if you have a need for sinusoidal wave raw, you can get it. But the majority, 95% of the incremental encoders you run into are going to have this square wave looking signal. So that's the basics. Any questions on like what's Jared talking about? What's an encoder?
So Jared, we do have 2 questions, and you might be addressing these, but what is the life expectancy of the bearings and what type of side force can they withstand?
2 great questions. The bearing life is a very important variable, and I encourage you always to look at it on the data sheet. Many of our encoders live to 10 times 10 to the 9th, 2 times 10 to the 9th, or some of them are 1.3 times 10 to the 9, so millions or tens of millions of revolutions. Other encoders out there, specifically if, you know, I don't want to name names, but low-cost encoders out there, if you look at the data sheet, you might see, you know, times 10 to the 6th or times 10 to the 7th. That's a very important consideration because the bearings are your most likely point of failure just by wearing over time, number of revolutions they're rated for. There's also loading considerations. Bearing life on our data sheets and most encoder manufacturers' data sheets that make high quality products, they are assumed with half the shaft load. So our shafted encoders, many of ours take 80 pounds axial and 80 pounds radial for shaft loads. Some of our light, very small, 1.5 inch diameter encoders, they get down into that 5-pound range. So with bearing life, you can go, well, if 80 pounds is the max, then if I do 40 pounds, I can expect to get that number of revolutions that's on the data sheet. Obviously, if you take a shafted encoder that's rated for 80 pounds max and you put 80 pounds on it, you're going to shorten that bearing life precipitously. Our MTBF math that we've done is all of our models are expected to last 20 years. And encoders, when treated well, made by anybody who makes quality encoder, you can expect them to last for decades. We get encoders back all the time from the 1970s and 1980s to this day that people are looking to just now replace. So treat them well. Those bearings will last a long time, and there's really nothing else in there that can fail.
And one more question, Jared. What type of encoder would you recommend for a high vibration application or skid?
We're going to get to that question a little bit when we go over mechanical packages, but when you get into high vibration, you want to isolate that encoder from the vibration as much as you can. And it depends if that vibration is coming through the shaft or if that vibration is the whole machine is going to kind of direct you. If you're vibrating on the shaft, you want to get a shafted encoder of or anybody's and put a helical coupling of some kind that will absorb that vibration between the encoder and the shaft. If the whole machine is shaking, you'll want to get a through-bore encoder so that the encoder is mounted to the shaft, but it's actually floating on a sheet metal flange so that it has some resistance to the total vibration of the machine. And I'll show some pictures of that in a second. All right,
Right.
so this second section here is the real meat and potatoes of the whole presentation. The incremental encoders are 90% of our business. We are going to talk about absolutes today. They have their place, but the majority of the world, it is still an incremental world. And in new applications, specifically AGVs, AMRs, mobile equipment that aren't on a CAN bus, incremental encoders are still widely chosen for new projects. So I'm going to go over those signals now of how an incremental encoder works. When we're done with this section, you're going to know everything there is to know about the signals of an incremental encoder, because they're not rocket science. They're not overly complicated. They're very simple and straightforward. So we discussed that LED goes through the disk, creates light. We make it into a square wave from there. If that disk had 1,000 lines on it, we would expect 1,000 pulses that look like this. So we have a rise. You know, if we have a signal that's 0 volt to 5 volt, we have a 0 to 5 volt rise. And then we drop down, and this is one wave right here, one pulse from this rise to the next rise. You would have 1,000 of these if you had 1,000 lines on the disk. So when you're speccing your encoder and you choose your resolution and you choose 1,000 CPR, you'll see counts per revolution. You'll also see PPR, pulses per revolution. That's referring to the number of these pulses. Now, when you get those, what can you do with them? Well, you can count them, right? They're flying by because you're spinning the encoder on something, and you can count them and divide by time. Now you have a velocity, or you can position. You can say, well, I've seen 500 pulses. I know my encoder's gone half of a revolution, and that means I've gone this far. You can, one thing you can't do is this is called single-ended output. On a data sheet, you'll see the word single-ended or unidirectional. When you're counting these pulses flying by, one thing you can't tell is what direction you're spinning. Whether I read these from right to left or left to right, it's just a rise and a fall again. So if I have that encoder on a machine and I turn it clockwise or counterclockwise, their pulses, they look the same. So its single-ended output is for one direction movement only. If you have it on a conveyor or a cut-to-length application or a belt, and that belt will never go the other direction, this is all you need. You need an encoder with one channel output, a 3-wire encoder, it's commonly called. But what if you have an application, CNC machine, for example, where you have a back and forth? Maybe it's a cut-to-length, but you need to be able to reverse the material to prevent scrap. You need to add a B channel. So in the 1970s, let me get out of my pointer here. The sensor was adjusted. There we go. The sensor was adjusted on the disk and added an offset sensor. So if I had 1,000 lines on the disk, I had 1,000 of these A pulses. I also now have 1,000 of these B pulses coming from another sensor that's offset. As you can see, the A channel is going high before the B channel goes high. The reason for that is to get direction. This is called bidirectional output. So now we've got 4 wires, voltage common, A and B. 1,000 pulses on A, 1,000 pulses on B, but B is offset from A. Well, why does that matter? You're going to love my PowerPoint art here. The reason it matters is if I turned the encoder clockwise, A would rise first. This is called A leads B. You look at a data sheet and it'll say A leads B clockwise. This is what it's referring to, that the A rises before the B rises. But if I go counterclockwise, it looks like that because I'm reading from the other direction. So your PLC control readout, digital readout, when it's receiving this encoder and the signals are coming in like this, it'll say, okay, add, continue to add up. But as soon as the signals look like that, because it swapped direction and B rises before A here, we have B and then A, your PLC control, whatever, is going to know, okay, subtract. So, oh, it moved out, oh, it came back, and this is subtract. B leads A. So that's the purpose of bidirectional output. Once that happened and people developed this two-channel output with the offset there, they realized, well, if we offset that 90 degrees, we can actually take these channels and looking at A, we have a rise on A when, starting with a rise on A here, about 90 degrees. If we look at one wave from rise to rise again as 360 degrees, and on a data sheet, you'll see that referred to as electrical degrees versus physical degrees of the encoder shaft. This is called electrical degrees. So we have one pulse is 360 electrical degrees. About every 90 degrees, we have a transition. A rises, then B rises, then A falls, then B falls. So some really smart person, I don't know who, said, well, if we treated each of those as a unique position, which it truly is, we could actually get 4 times the number of positions in a circle versus just counting the rising edge of A. Well, that led into what's called quadrature. So when you have a PLC or a digital readout or whatever, and you see that it has quadrature, the capability for 4x counting, edge counting, or quadrature, it's all the same thing. It's counting all the edges as unique positions, and it allows you, you'll have some that offer 2x and 4x. All the 2x is doing is it counts the rising and falling of A, which gives you 180 degrees apart, and you can double your number, or it'll count all these. If I had 1,000 pulses per revolution, I now have 4,000 unique points in a revolution. So it's a way to take an encoder and multiply its resolution by 4, get 4 times the number of points. Why is that an advantage? Well, a lot of encoders have a maximum resolution capability. I run into a lot of vision systems where, you know, Jared, we really need 24,000 pulses per turn. And well, this encoder only goes to 10,000, but we can do something, multiply it by 4 and get you up where you need to be. Another reason to do this is, you know, Jared, I have a max frequency on this circuit. I can't go above a certain amount. And I say, well, let's get to close to your max frequency, but do quadrature on your receiving end, and you can get 4 times that resolution without hitting the max frequency. Encoders cost more as well. As you increase the resolution on the disk, to print that disk costs more to print it because they're finer lines. And it also requires tighter air gap spacing. It's more to manufacture them. So when you buy encoders and you go up in resolution, you go up in price. So it's a way to save on the cost of the encoder and the machine design as well. Quadrature is all done on the receiving end. Nothing fancy is happening in the encoder. The encoder is just putting out A and B. This is all done on the receiving end. So a lot of people go, I don't see if you offer quadrature on your data sheet. It's not on the encoder. It's how you're interpreting the signals. So
Jared,
go ahead.
We have a couple questions here. How many RPMs can an encoder handle?
In theory, I guess infinite. The limits to RPMs are 2: the max bearing speed, and but not all encoders have bearings. Some encoders, which we're going to get to in the next section, are modular. You install the disk and the read head separately so that you don't have the limitations of bearings. At that point, your limit is just the frequency, the max frequency of the electronics of the encoder itself. So when I get into applications that are, 24,000 RPM robo drills, for example, and you know, an incredibly high RPM on a spindle, you will see those encoders are bearingless, and they use low resolutions. They may be, 256 or 512 or 1024 pulses per turn, so that when they're at 24,000 RPM, their circuit frequency doesn't exceed, the 500K or 1 megahertz or whatever of the system. So as long as you can handle the frequency and you're not exceeding any kind of bearing RPM, fast as you want.
And what type of preventative maintenance is required on encoders?
There's nothing really. The only thing is in your design. Encoders obviously have either shaft or hollow bore, and that's a sealed opening that allows for ingress. So if it's a washdown environment and you have, let's say, a through-bore encoder where the seal on the back is exposed, I encourage, putting up some kind of glass shield or covering so that you're not spraying water into it. But in reality, it's the design. You need to make sure, especially with IP ratings, that you're choosing the appropriate housing for the job. I just worked on another train application, and the encoders were failing up in the Arctic, inspecting railroad track cracks. That's why it's on my mind. I guess just happened. And that one was because the encoder they spec'd was IP50. So they were getting condensation, and then the condensation was freezing, and it was actually cracking the glass on the photosensor. So we've since changed that out to an IP67 encoder for them. That's nothing about preventive maintenance that you can stop once it's designed in. It's just why it's critical to choose the right package in the beginning.
Then
There is
two more
no that. Go ahead.
If you have a unidirectional encoder, but it's reporting more counts than actual, do you know what may have been happening?
Yeah, I pulled that section out. So we're not going to hit that one today. But if you, when you see more or less counts, if you have that now, I have a Y divider. And the question is it repeatable? If you're seeing extra counts, or if you're seeing missing counts, but it's the same amount every revolution, you probably have a problem with your disk. Either your disk is cracked, which can actually cause extra counts, or your disk has rubbed, the read head has hit the disk and rubbed lines off the disk, and you have a section in your revolution that's missing counts. If it's a problem with the disk, it will repeat every revolution. If it's random, if you turn that encoder and it's 100 counts and 500 counts and 33 counts, it's probably not a problem with the encoder. It is exceedingly rare. I've only seen it a few times, and it's usually caused by overvoltage, that the ICs go bad. So if you have random counts, high or low, it's probably noise, either a bad connection. More often than not, it's noise. Encoders do not like noise. We do get in with that today, how to mitigate noise. In fact, that's what this next section talks about as well.
And then one more question. If your encoder loses power or voltage and regains power, does it retain the position it was in and where it left off?
An incremental encoder will never, by design. Absolute encoders, yes. And our absolute encoders and a few other manufacturers now have a technology that if you lose power and you move the encoder, when you turn that encoder back on, it will still be reporting the correct position. That's a pretty recent new technology. Up until recently, encoders did have the ability to retain a position. If they lost power and turned back on, they still reported the correct position, but they wouldn't report the correct position if they moved while unpowered. So yes, you can get that from us and through a few competitors as well. It's called energy harvesting that we'll get to. Incremental encoders, that is the number one downside to an incremental encoder. It just spits out pulses. There is no memory. There's no serial communication. It will not, you turn that thing off and move it and turn it back on, it's just going to spit out A and B again. So you will lose position if you lose power. And a lot of CNCs that ran with servo motors that had incremental encoders, well, that's why when you lost power and that Z-axis dropped before the brake kicked in, you had to turn that machine back on, and the first thing you did was a machine zero because you lost position. Good to go?
Yep, thank you, Jared.
All right, so complementary signals. We realize that, hey, A and B, we have, if we put in, and this is just out of an IC, if we put in an inverse signal to complement each channel, so if we have a two-channel A and B, let's add inverse signals and call them complements. And now I've got 4 channels instead of 4 wires coming out instead of 2. Why do you see those? You'll see these on data sheets. I like A star because it's actually on the keyboard, but you'll see A with a line over it, A with a slash through it. I've even seen A and B just written upside down, which I thought was kind of cute, but again, hard to find on the keyboard. They're often called knots or complementary signals, and they're the inverse. The reason for these signals is noise rejection. That's it. It looks like a spaghetti map here now. They're not doing anything except help mitigating noise so you don't see those extra pulses or lost pulses. Reason being is if I had just A here, just an A channel, and this was on a machine next to an air compressor, that air compressor turns on, it makes a ton of electrical noise, and I have a 30 volt spike over 1 millisecond right here. You know, the voltage is going along, and all of a sudden I got a spike. Well, if I had just A channel, that spike went above 5 volts, guess what? Pulse. My receiving electronics are going to call that a pulse, and I've now lost my position, or I've got a bad speed reading, right? Well, when you add these knots, this is called differential output. So when you see an encoder, or more specifically, you're choosing your receiving device, if it accepts differential output, you'll want to take advantage of that. In our encoders and most of our competitors, we don't charge any extra to get the complementary signals. What this is because I now have a signal that is always the opposite. In differential encoders, the receiving electronics are measuring the difference in voltage between the two channels to determine when a pulse hits. When I have just A, it measures at half the voltage. So if this is 0 volt and 5 volts for high and 0 volts for low, think of a 0 and a 1. If this channel ever exceeds 2.5 volts, once it hits 2.6 volts, my PLC is going to call that a pulse. So when I have that spike in voltage, it's a pulse. Well, when you have differential output, it's measuring the difference between the two channels. A is 0, A naught is 5. When A goes to 5, A naught goes to 0. And it subtracts one from the other, and that's how it knows if you've pulsed. Well, when I have that noise, if I have a 30-volt spike here for a millisecond, I'm going to have that same spike on the A naught. They're in the same cable. Because I'll have noise will affect all the channels equally, they will still have the same difference between channels. And that's how you can reject noise, the purpose. How we recommend it anyway, everybody's got a little bit different, but they're all about the same. Manufacturers, if you're running more than 30 foot of cable, you want to run complementary signals. If you're working in a warehouse, stretch wrap machines, anything with a lot of static, just don't even play around with it. There's, again, very often there's no cost. With us, there's no cost to go to a complementary output. Your cost increases only in the cable. You're going to have to run cable with 2 more conductors, but highly worth it for rejecting noise. Then the last thing with incremental encoders is this third pulse you'll often hear called an index or a home or a reference pulse. Most data sheets call it a Z pulse or a Z channel. And what that is one little line scratched on the disk that goes off once per revolution. So I'll have 1,000 pulses of A and 1,000 pulses of B, but 1 pulse of Z. If I were to turn my volts per division knob and the oscilloscope there, zoom out, and I had my whole revolution, 1,000 pulses of A, 1,000 pulses of B, this is what little Z looks like. That's often used for home or indexing. If it's on a CNC machine, your table will rapid to one side to zero out. It'll hit a limit switch and then it'll creep. And when you see that table creeping, what it's doing is it's looking for that very specific point in the revolution, which is the Z pulse. So that's why you'll hear it called a home signal a lot. One purpose it does serve that's often overlooked is error checking. And many VFDs will utilize a Z pulse on an induction motor. If you put an incremental encoder on an induction motor, I encourage you to get it with a Z, because what the VFD will do is, if we know we have 1,000 pulses on this disk, well, then we know that every time we see Z, we can reset an internal counter, which is what they do in the VFDs, and we should count to 1,000 before we see another Z. So if we start counting to, the person who asked that question, if we start counting to 1,100 and then we see the Z, that VFD is going to trip with a PG alarm, a pulse generator alarm, or an encoder alarm, feedback alarm. And that's because it's going to go, we got a problem. This encoder is not putting out 1,000 pulses per revolution. It's not working. So the Z pulse, even though it often gets thought of as a home, and that's what it's often called, it's also a great tool for error checking. Outputs. There's a lot of confusion with outputs. There's a lot of choices out there. We have electrical engineers on staff. They probably spend half of every day just helping people choose the right outputs. I'm not going to go into the nitty-gritty of these electrical diagrams, but I want to give everybody a general idea of what they need. There are 4 main types on almost all encoder manufacturers: open collector, pull-up, push-pull, and line driver. If you're using a simple NPN type setup, you want open collector. Now, these actually divide into 2 groups. Pull-up and open collector here. Let me get back my spotlight. Pull-up and open collector are pretty much the same thing. If you look at the circuit diagrams, they're identical here. We're using our transistor. We're connecting a channel through the transistor. It's an open or closed switch, and it just returns to common. And that's how you're sensing that pulse. What's unique about the 2 with everybody is that you need a pull-up resistor in an open collector type setup to see these square wave pulses. Well, if you're designing the system, you're probably going to want to choose a specific resistance for that pull-up resistor for rise time, how quickly it rises, or what final output voltage you want. So you're going to order open collector because that pull-up resistor is installed on the receiving end where you put it in. But sometimes maintenance items, or if you don't really care what the pull-up resistance is, 2.2 kilo ohm is very popular. That means we install it. So you just slide this thing down to Encoder product side, and we put it in for you to eliminate that headache. So the only difference between open collector and pull-up is you supply the resistor or we supply the resistor. Maintenance people, I was in maintenance for many, many years, working on the road in service, and you really can't go wrong with a little extra resistance on the pull-up resistor. So very often I would just always cross it to a pull-up so that it was in there. If you don't have a pull-up resistor, you won't quote-unquote see the apparent voltage of the channel. So if you hook up an open collector encoder and you go, I'm not seeing any pulses, chances are you don't have a pull-up resistor in there and you got to put one in. Push-pull and line driver, back in the day, even in the early 90s when you ordered encoders from a variety of manufacturers, you put the line driver. You would choose an 8383 or 7840. You put it right in the part numbers, very specific. Those days are gone. Most encoders that are push-pull, sync and source, you'll see it called, or line driver are all actually using a line driver chip. In fact, our encoders, our push-pull and our line driver use the same IC. The only difference between the two now, if you have a sync and source, you can use push-pull. Even PNP, you can use push-pull or line driver. The difference you'll find is that typically push-pull offers just the channel itself. So in this example, it's just A, but if you want those complements, we were talking about noise rejection. If you want those complementary signals, you're going to run with the line driver option, it's called, to get that complement. So we have A and A not by choosing line driver. These from us and most people are the same price. It's if you want the complements or not. If you're on a maintenance side of things, you're not sure, order the line driver. If you don't end up needing to wire the complements, just cut them back so they don't short out. If you're an OEM, you're designing it in, you don't need the complements. Why have a wire that could get mishooked up and cause you problems? Order the push-pull. You know, I encourage OEMs that really don't need complements to go with the push-pull. But on the end user side, you're not sure what you need, you don't have to wire them up for it to work. Just make sure you don't short out those complements. They're there if you need them. So the benefits of incremental encoders, they're cost effective. You know, I just off the top of my head, I have no scientific research behind this. I would say they're between 40 and 50% the cost of an absolute encoder. That's not going to change. They're just a simpler design. So they're a very cost-effective way to get highly accurate feedback and positioning on your system. Even, which we're not in this world, but if you look at the rotary scales that are out there that have 4 million points in a circle for a rotary table where you're positioning to, you know, 3 or 5 micron, inside, they're incremental encoders. They're just lines on a disk. They're very high response time. So if you're doing very quick motions where you need to position quickly, you have a very high frequency response. Generally, it's in the nanoseconds. So where that encoder just told you it is, it actually is. Absolute encoders and fancier encoders, if you will, that have serial outputs, can open SSI, you know, Profibus, whatever. They're going to have much slower response time, generally in milliseconds. And it's because you have a back and forth talking that needs to happen and checking packets and all this. So you will never get the frequency response from a serial encoder or an absolute encoder that you get from an incremental encoder. They're very simple to set up. AB channels have been around, like I said, for over 50 years, decades, and most devices accept, you'll see quadrature, differential, all the different ways to say it, they will accept incremental signals. So it's very easy to set up and find a device that'll take it. They're incredibly reliable. The failure is the bearings. That's your biggest point of failure is those bearings going bad, or disk crashes if you're modular. Drawbacks. You lose your position. It shuts off. It just puts out pulses. It doesn't know where it is. There's no brain, if you will, in an incremental encoder. So if it's critical, especially in a safety application, that you cannot lose position during a power loss, incremental encoders are not the way to go. Accumulating errors, noise, if noise gets through and your receiving device is counting ghost pulses from noise that aren't there, or missing pulses because the disk is scratched, you don't know unless you look into it. There's no way for that encoder to say, I'm putting out bad pulses. So there's a possibility to accumulate error over time, and that can add up. In an application where that encoder is constantly running. You'll have a CNC machine. This thing's 1,000 off every week, and then 2,000, then 3,000, then 5,000. Could be noise, and the encoder's not going to tell you. Also, when you turn on an incremental encoder, the position is unknown at power on. It puts out pulses. When you turn it on, it is not a wristwatch. It doesn't tell you it's 230. It just says pulse, so you don't know where you are when you start up. If that's critical, you need an absolute encoder. So now we're going to go over the fundamentals of absolutes. Any questions on that? That was the big thick one for this presentation.
Yeah, Jared, I knew this was going to come up, and I know you do cover it, but do you offer any Ethernet encoders?
Ethernet, yes. We offer, Encoder Products offers EtherCAT that will go on a standard Ethernet or a back-off EtherCAT setup. We also offer Profinet. So if you have Siemens type products, we have a Profinet encoder that'll work on those systems. We do not have Ethernet IP yet, another common Ethernet protocol that works with Rockwell products. That's in the works, but there are encoder manufacturers that have that. Those are the big three for encoders on a network. There's tons of bus protocols out there, but for networks, CAT, Profinet, and Ethernet IP are the big ones.
That's it. Thanks, Jared.
Perfect. So now we're doing absolute encoders. So incremental encoders put out pulses. You don't know where they are. They just put out pulses. Absolute encoders tell you where they are. They actually say, if it's a watch, hey, it's 2:30. You could look away from it for half an hour, look back. All right, it's 3 o'clock now. You didn't have to watch that minute hand move past every minute to know it's 3 o'clock. Wikipedia says it best that digital absolute encoders produce a unique digital code for each angle of the shaft. So each unique angle of that shaft, it puts out a binary code for that position. That's how it knows where it is. So the benefits of an absolute encoder is when you power it on, it will tell you where it is. It'll say, I'm at 30 degrees as soon as you turn it on. You don't have to move it and start counting or zero out to get that position. They can correct position if there's noise or if the signal's interrupted. If an absolute encoder is putting out signal and all of a sudden you have a cable drop or noise, a garbled signal, if that is reestablished automatically, that next signal that's read correctly will be the correct position and will update the system. There's also the potential for multi-turn counting for very accurate continuous positioning over a long distance. Multi-turn counting means not only do you know your position in a circle, but you're also counting the number of times that encoder turns. My train application, I'm going to go on that one today, stuck in my head, is that's exactly what they're doing. They need a unique position on that railroad track for where the cracks are. Well, that wheel's going to do hundreds of thousands of turns to go from, Connecticut, where I am, up into Canada. So they need to know not only where in a circle that crack is, they're looking to get it to half an inch. So where in a circle that crack is, but how many times that's gone along to tell us that crack exactly where it is 100 miles from here. So multi-turn counting is a big part of some absolute applications. This is an example of an absolute encoder wheel here. This has tracks. So unlike incremental encoders that just have, my pointer here, that just have lines on the disk, absolute encoders have tracks, kind of like a record, right? This encoder has 3 tracks, 1, 2, 3, that are being used here. You would call this a 3-bit encoder. And what it does is if the light's going through, it will call each bit a 1 or a 0 based on if a photoreceiver detects light or not. So unlike an incremental where you had that one photoreceiver, there's actually a photoreceiver for each track. And if light is going through, it's a 1. If light is not going through, it's a 0. Now I realized that I did this in paint and I made the black thinking that was a hole, but once I put it on the background, it kind of looks like this should be where light's going through. So I'm going to change those. But if we treat this as a hole and light is going through, we would call that a 1, right? So this track here, if this was a spinning disc and this is where my current position was, I would say, okay, I'm at 1, 0, 0. That's the position. If I rotate the encoder a little bit, we interrupt the light differently. Now I have 1, 0, 1. That's this unique position. So with a 3-bit encoder, I've got 8 unique positions. Not a lot of positions, but that's how it works. They're each unique. So if I turn the encoder off and move the disk to here and turn it back on, I will still be giving out the correct position because it's going to give me out that code. That's how they work. That's it. That's an absolute encoder. If we zoom this out, let's look at a 10-bit disk. This is one of our disks for a 10-bit feedback. You've got an array of photodetectors. And if the light's interrupted, it's a 0. If the light's not interrupted, it's a 1. So we'd have, 1, 1, 1, 1, 1, 0, 0, 0, 1. That would be this unique position. And this encoder would give you 10 bits of positioning. Any questions with that?
Nope, we're good.
All right. So that's it. That's the meat and potatoes how an absolute encoder works. Now, when they were, my 3-bit disk here, this is an 11-bit. This is our model 960. As you can see inside, it just has those photo receivers, which are right here on this metal plate. And it's just shining light through. The light actually is above. That board with the LEDs taken off. But this is the receiver. And it's just counting the light or not of each unique position. Well, that's a lot of tracks. So the old absolute encoders, back in the day, as they say, used what was called parallel output. And all parallel output meant was which is what this encoder here is, there is a wire for every channel. And that wire has 5 volts on it, square wave, 5 volts or 0 volts. So if you had an 11-bit encoder here, you had 13 wires coming out of that encoder, voltage common, and 1 conductor per bit. And then that would go to your receiving electronics and taking that parallel output. That's a lot of conductors. Well, a lot of encoders nowadays, on servo motors especially, they get up to 19, 21, 23 bit. Who wants 25 wires in a cable? That's a problem. So nowadays, you're going to get absolute encoders that put out in bus protocols, or that question there with Ethernet protocols, those are there as well. That is to eliminate these gigantic bundled cables of having 1 conductor per bit. Now I can take 23 bits of single turn information, and I can put it in a protocol and still have a 4 or 8 wire encoder. Common protocols out there, SSI, can't open, there's IO-Link, Modbus. I mean, it's the Wild West with protocols right now. And they're going to add lots of fancy things and charge a lot of money for fancy boards. At the end of the day, all that's happening in there is the same technology. It's a code disk that's creating binary signals and 1 binary output per track. And then the top board is just digitizing it, serializing it for the method you need. Here's our network protocols. EtherCAT, Profinet, Ethernet IP are the big ones right now. Well, this is the one we don't have yet, but it's in development. These are the 2 we have, but there are others that have this. So you can get all 3 of these. You can get encoders from manufacturers or from others that offer these outputs. If you have an application, I've had a few where these would be handy, especially long cable runs, and you just want to stick it on a network versus running a 200-foot cable to something. They're great products. The downside to these right now is they're very expensive relative to other encoders. Many of these get over the $1,000 point, $800 to over $1,000 point list. The other downside to network encoders is they can be very slow, like not even discrete. Some manufacturers out there have data sheets that spec out their response time to 125 milliseconds. So that encoder hits a position, you're waiting 125 milliseconds before you know it actually got there. That's a problem if you're discrete positioning. So there's some big downsides with network encoders, but some big upsides that, hey, I can just put this to the network and avoid the middleman. Applications that would require single turn. So I hit on single turn and multi-turn a little bit. Just want to touch on these one more time. A single turn application would be like this: a tool changer on a CNC machine or an antenna. These we need to know the angles of. We're lining up our collet to our tool changer to change the end mill out in our spindle. And we need to know the position within a circle. We don't care how many times it's gone around. We just care about the position in a circle. That's where you need a single turn encoder, an encoder that only puts out a binary code for its position in a circle, the disk I just showed you. And this antenna, same thing. If it's a Doppler antenna, it's picking up, hey, there's a tornado. Well, I need to know what direction I'm pointed at. I don't need to know how many times my antenna all does go around all day. I don't care about that. I care about the angle. So I need a single turn encoder to give me that angle. But sometimes you do need to add up the number of turns. That is a multi-turn encoder application. So here we have a gantry crane. We've got a pointer. We've got an induction motor here with an encoder on the back. Well, this motor is going through a large gearbox that drives this gantry crane up and down the gantry. So this motor may do 1,000 revolutions to get this crane from one end to the other. So if I'm positioning it, I need to know not just the position in a circle of that encoder, but the number of times the encoder's gone around to drive this crane. So if it's 1,000 revolutions to get this gantry crane from one end to the other, then I know, hey, I've gone 500 revolutions, I'm halfway. That's why you need to do multi-turn counting. And when it puts that information out, it just adds it to the bit. So if I have an 11-bit encoder and then I have multi-turn counting, it just becomes one long position value. Our encoders go out to 59 bits now of information. Imagine having a parallel output for that, 61 wires. So 59 bits of positional information. Just to give you an idea what you could do with that, you could actually put a 12-inch wheel on one of our encoders, 12-inch circumference wheel, like you're lining a soccer field, and you could walk to Mars and back 25 times before you rolled over to zero and lost your unique position. So absolute multi-turn encoders out there now can give you discrete positioning over very large distances. This train company is going to have a unique position from where they start to where they end, even if they go across the continent. This is a table, same idea, that if we have a servo motor with an encoder on it, that encoder is giving a position, and that motor is going to drive this shaft more than one revolution. It's going to be multiple revolutions to move this table from one end to the other. So we need to know the number of turns plus its position in a circle to know the location of this table. There are other types of absolute feedback out there to keep in mind. These are not encoders, nothing we make, but they can be used for absolute positioning. Some of them may surprise you. Resolvers are one. These are wound transformers. I have a lot of experience with these. These are still the most accurate rotary transducers, you'll see them called, most accurate feedback out there. They're basically an analog feedback. You're inducing a current into one coil, it excites these coils, and then you read the output of the excited coils. And it gives you a position. It's as accurate as you can reduce noise, which is its drawback, is incredibly susceptible to noise. But resolvers do have an advantage. They can go to about 210, 220 C. Most encoders out there melt at about 130 C. So if you have an application where you're looking at getting positioning within a very hot area, resolvers are a great choice for doing that. You'll have to mitigate the noise problems, and they're a little pricier for the receiving electronics to do that, but they're a great alternative for high temp. I had one application that I just pushed a customer to a resolver because it was an oven for a chicken nugget cooking machine, and it was just too hot. And why try to make something fit that doesn't? So that's a great solution for that. You'll see a lot of devices out there to offer 4 to 20 milliamp output. You know, and if it's a linear application, it might be 4 milliamp at one end and 20 milliamp at the other end, and it's a linear progression. That is a current output. That's an absolute position. Whatever that current is, it's equal to a position over that distance. So that's a lot. You'd call that an analog device, and there's a lot. Encoder Products does not offer that, but other encoder manufacturers do, and that's a great tool for when you need typically shorter distances, but you want a very simple analog output to accomplish an absolute position. There are devices out there that just use potentiometers. If this were a single turn potentiometer, 0 volts on one end, go 340 degrees, and I'm 10 volts on the other end, and it's a linear progression, you can use that output for an absolute position in a circle. Obviously, there's some downsides. You know, mechanical failure, it's a contact device, there's a little wiper on the resistive board there. So there's some downside, but they are very simple and cost effective. Any questions on that, on absolute encoders?
We're good.
All right. Mechanical packages, asking about vibration. Encoders, most of our encoders, not all, most of the encoders out there are what you call integrated bearings, encoders with integral bearings. And they come in shafted options and through bore options. They're generally a higher cost than encoders without bearings, and what you'd call a modular or a kit encoder, some people call, because they have the bearings. They're more robust, though, to misalignments. So if you're putting these encoders in an application where there is going to be misalignment or shaft runout or high vibration, you'll want an encoder with bearings. The reason is by having bearings, we have a bearing on the shaft. Inside this encoder, we just saw a picture, right? There's a glass disc on the end of this with a reed head. That glass disc has got to stay central to that reed head. If it runs out just a little bit, you're going to introduce inaccuracy, and then you're going to crash it. So there's a nice set of bearings in here that keep it all centralized. So that way, even though there's vibration or run out, we are going to have that disc distance to the reed head maintained. Now, shafted encoders generally take a lot more shaft load. This model in the picture here is the model that takes 80 pounds axial and radial. So they can take a lot more of a beating. Generally speaking, if you have a lot of vibration on a shaft, I recommend running with our shafted encoder and then choose an appropriate coupling. We sell helical couplings, but there's other options out there. I've seen Lovejoy's used with a spider if there's a lot of axial end play in and out. Couplings are a whole science in themselves, but you'll want a coupling here to just isolate that shaft from the vibration of your shaft. If you have it, let's say this is on, what's an example I did? A concrete vibration machine. It actually vibrates concrete at specific frequencies to make a very specific textured concrete. Pretty interesting. That machine, man, it can vibrate. Holy moly. So they ran with through bore encoders that sit on a sheet metal flange. So this bolts on the shaft. Now the disc is hard mounted. It's going to move with the shaft. But the housing of the encoder is going to move with it as well, and it's going to shake on this extremely flexible spring. The encoders can tolerate quite a bit of shock and vibration, and that is on most quality manufacturers will admit to their values and put it on our data sheet. It's on our data sheet and our competitors who make quality products, so that you know what it'll tolerate for shock and vibe. They can take a lot. So again, yeah, if you're vibrating the whole machine, I recommend this. And if you have a vibration or run out on a shaft, you'll want to put a shafted encoder on there. The bearings in these through bores are generally less rugged because, as you can see, it's a larger ID on the bearing. It's going to be a smaller ball set in the bearing. So as far as axial loading and shaft loading, through bore encoders are always going to be less rugged than shafted encoders. You got a nice small ID, so you got a nice big ball set on that bearing. It's a really rugged bearing. We design our encoders that regardless of the bearings that are in there, the loading on this is less, but the loading we rate it to, we expect it to last for 20 years with that standard load. Modular encoders or kit encoders. They're generally less expensive, not always, but generally. So if you're looking for a low-cost option, a kit encoder is the way to go. They'll also handle higher speeds. You're not limited by bearings. You know, a lot of bearings are limited to 6,000 or 8,000 RPM. If you need to go 10,000, 12,000, anything faster, you're on a spindle, you'll want to go with a modular encoder. They're more complex to install. That's the trick. The hub, you know, whether it be this is an optical here, this is an optical encoder. You've got a hub that's going to bolt to your machine, and then you've got a disc that's going to hard mount to your shaft. This is unforgiving. It's moving with the shaft. This is unforgiving. It's moving with the housing. If there's any run out, you're going to destroy that encoder in a second. So I don't recommend these. If you don't need one of these advantages, hard stop, I need one of these advantages, I don't recommend modular encoders for that reason. There's no forgiveness to vibration or misalignment. They're at the mercy of the machine. But you have those amazing advantages of high speed, or you're not worried about bearings, and lower cost as well. Wheeled encoders. This is our Model 15T. We put a dog bone arm in it. It's got a nice internal spring for applying pressure, and we put a wheel on it. So what can you do with wheeled encoders? Well, now we're taking a device that up until now I've talked about a lot of rotational applications. You can use these for linear measurement. Common applications for this, vision systems, AGVs. I have AGVs that run this on the floor. I have AGVs that use forklifts, AGVs, that use a gear on this and do a rack and pinion for the height of the telescope. Anywhere where you need linear positioning, where maybe the cost or the application doesn't warrant a linear scale to get a distance over that length, you can use a wheeled encoder to run on. These wheeled encoders will run on the product, they'll run on belts, and they'll give you a distance. How they do that is, hey, this wheel here is 6 inches in circumference. So every rotation, one exact rotation, is exactly 6 inches of linear distance. If I have a 6,000 pulse encoder, if I have a 6,000 line disc in here, I now have 1,000 lines per inch. So this encoder will give me a pulse every thousandth of an inch. That's the advantage. That's how you use a wheeled encoder. Now, the downside of wheeled encoders is they don't like changing direction. It's a rubber wheel. If they're rack and pinion, they do. The forklift, they do. But most applications use a rubber wheel, and if it's a two-directional thing, you're always going to have a little loss on the reverse. I have a lot of inkjet printers that use this. They zero out every single cross of the y-axis. That's how they get around it. But there is another way to use an encoder in a linear aspect where you can do two-directional measurement accurately and repeatably, and that's with a draw wire. So take a rotational encoder, spins with pulses, put a drum on it with a cable. Now this drum here is 5 inches in circumference, or actually the cable itself, the cross section of the cable is exactly 5 inches when it does one spool on this drum. So if I have a 5,000 line encoder and I take out 5 inches of wire, I will have 1,000 pulses per inch. So I can get to 1,000th of an inch, and for every 5 inches I pull out will be 1 revolution of this encoder. I can do linear measuring. This draw wire here is one of our shorter products. It goes to 50 inches. There are draw wires out there that go to 40 meters. We have, I think our highest in the line card we're adding right now is 42 meters. There's some I've seen made in Canada that go to the hundreds of meters. What are they used for that length? My latest application is an injection mold machine. One advantage of draw wire measurement, using an encoder for linear measurement here, is you can take the electronics away from vibration and away from heat. In the case of an injection mold machine, they're mounting this to that sled that the injector's on, injecting the plastic. Now they can move this encoder many feet away from the heat of that injector so that they're not cooking the electronics anymore. The forklift application, I've seen these used. In fact, I bet more forklifts are using draw wires now than are using rack and pinion. And it's because it's repeatable and they can put it in the base and my encoder isn't moving with the telescopes. They are a very cost-effective solution versus linear scales. Linear scales are very expensive. Really the only reason left to use a linear scale is if you need extreme accuracy. Obviously, especially in a horizontal application where there's gravity, there is some loss of accuracy. They're still highly accurate, 0.02% linearity. It's very accurate. It's accurate enough to position an injector head on an injection mold machine. But that's where they're typically utilized. That's typical mechanical packages. Any questions on those? All right, I know we're running out of time here, so I want to go over real quick some application considerations. Frequency is a big one. Frequency can be a killer for 2 reasons. One, you exceed it, you're going to get bad pulses. You're all of a sudden going to see it won't level off, it'll just go erratic. So you want to be conscientious of when you spec an encoder, what's the resolution I'm using and how fast am I spinning it? Take those 2 variables and figure out your max frequency. We have a calculator on the website to help. If the other consideration is temperature, the higher frequency your encoder is, the higher temperature it's going to generate internally. It's the switching. It's the switching of the 0 to 1, the 0 to 5 volt, or 0 to 12 volt. That switching generates a lot of heat on the ICs. So the higher your switching frequency is, the higher you're going to generate temperature. So if you have an application where you're going to run an encoder high speed and you want a high resolution and the environment's already hot, you're going to want to pay attention to that. Most encoder manufacturers, we have no way to know what all 3 of those variables are. So when you see a maximum value on our data sheet, it's assuming everything else is normal. It's assuming room temperature, it's assuming the max RPM, but room temperature. So if when you're doing that, if all 3 of those are high, you're going to want to pay attention to that frequency and call us, and we'll let you know what you're able to do. Accuracy is another one. When you're specing an encoder, I'm just not getting enough accuracy out of this encoder, you're going to need a different encoder. Adding resolution to a disk does not increase its accuracy. It just increases the number of points in a circle. Accuracy is that encoder position actually where it's telling me it is? If it's telling me it's at 10 degrees, is it actually at 10 degrees or is it at 10.5 degrees? Well, it's just that this system is just a little too inaccurate. I need to get more resolution so I can get more points in a circle. Nope, that won't work, because if it's 0.5 degrees off, every line on that disk is going to be 0.5 degrees off from the true position. You need to get a more accurate encoder. All high quality encoder manufacturers, I can't believe some of them that I don't see this. I mean, you're buying the thing to accurately measure something. There are encoder manufacturers that don't put it on the data sheet. Most do. You're looking for this information. The encoder, I took this off one of our data sheets, is good to 47 arc seconds. There are some encoders that get all the way down to 5 arc seconds, or 3 arc seconds, or they may have it in microns. That information is very valuable depending how accurate you need to be. Generally speaking, when you get down to the very tight accuracies of 5 microns, you're talking very expensive rotary scales. They won't even call them encoders anymore. Temperature, the type of disc that you use, whether it be film, glass, or magnetic, that affects temperature. Film discs are great. They never break. High vibration environment, ask for a film disc. Then you don't have to worry about a glass disc cracking. Downside to a film disc, they melt. They melt at low temperatures. They're unbreakable until they get hot. So pay attention to the disc type. Magnetic discs are higher rated for shock and vibe. We have magnetic absolute encoders. Those discs have a higher shock and vibe rating than our glass discs. The downside to magnetic technology is it's not as accurate by about a factor of 10. It's not as accurate as optical technology. So you're going to want to pay attention to your sensor type and your disc type. And the temperature of that field affects that decision. Noise considerations. Make sure to choose the correct output type for the cable length. Longer runs should be a line driver with differential output, as we discussed. Use shielded connections if you can. Make sure that you're properly draining those shields to ground. That is critical with encoders, that you're draining them. You know, a lot of people worry about, I don't want to make an antenna. I don't want to connect it at both ends. That is a good thing to try to avoid. But honestly, the 95% of the problems I see in the field is the encoder's not properly grounded. And a lot of people don't realize that they use a bore sleeve and a through bore or something, that they're not properly grounding to the shaft, that spring spacer mount, we actually ship it with an insulated bushing. They're not grounded through the spring spacer that mounts the housing. And well, I didn't want to hook up the shield because I would have created an antenna loop, and I go there with a multimeter and say it's floating. It's not connected anywhere else. So you want to make sure that there is a clear drain so that you're not getting erroneous pulses on that encoder. Utilize twisted pair where appropriate, especially for longer cable runs. That can be more money. Twisted pair cable is considerably more expensive than straight cable, but it's worth the cost if you're worried at all about noise. If you're in the material handling world, you're worried about noise, and you'll want to consider that. And then signal repeaters. If you're going with any incremental encoder, especially if you're running at a 5 or 12 volts, if you're going over 100 feet, I encourage you to get signal repeaters, because there's just enough voltage drop over runs of more than 100 feet. That's where you start running into issues with noise and loss of signal. Any questions on those? All right, so we're going to go through our last section here. We have applications examples, induction motors. This is an induction motor that you'll find all over industry, conveyor belts, things like that. And nowadays, whether you're designing a new application or you're retrofitting or upgrading something in your plant, you're going to find the need that, hey, we used to have an induction motor with a little VFD and a potentiometer, and hey, make this line go faster. Okay, and you turn the pot up. Well, now you've got robots, tending lines. You need to track those lines. You need to maintain the speeds of those lines with a feedback loop to control it. So a lot of applications now are asking for induction motors that have feedback on them, or induction motors in the field where you need to install feedback. We sell a variety of encoders out there that you can adapt motors with subshafts that will mount directly to fan shrouds, or have NEMA mounts to go to the back or the front of induction motors. That is becoming one of the most common applications for encoders, even more than it used to be. And encoders have been on induction motors for a long time. Many motor manufacturers out there have a limited selection of encoder options to come on the motor. So very often that's where we're still getting brought in, is even though that induction motor manufacturer offered feedback because you had a specific need in that application, you're going to want to buy secondary encoders from somebody else and adapt it and mount it to your motor. Conveying belts. This is an example of a linear application. We have a wheeled encoder here. This wheeled encoder is running on the belt. This is a cut-to-length application, cutting PVC pipe. And they're measuring off the product. The PVC pipe was too slippery, so they actually are measuring right on the belt. And that is still an accurate measurement where they were doing 10 or 20-foot cut-to-length pieces, and they used that encoder to get that. And this encoder was bidirectional. They could actually back this pipe up, and if they overshot and not have scrap. This is an example of a wheeled encoder, again, doing tracking. This I stole from the Automate, took the picture. This is the Automate booth for Omron, and Omron is using our TR1 wheeled encoder on a belt. So they had a scanner scanning these candies going by. Well, this arm that was picking these candies off the line needs to track them. So they use our encoder to create pulses to know the position of each candy with a tracker. This is another example of a wheeled encoder, and this is one you probably haven't thought of, but it's been very successful. Large bore. This is an escalator I worked on in Washington, D.C. Most are escalators. We're using a setup like this, very nice encoder, not ours. But they were taking a screen door from Lowe's or Home Depot spring. They'd taken a piece of angled aluminum and self-tapped through the housing of the encoder to hold a wheel against the shaft. Why were they doing that? They were doing that because this shaft is huge. This wheel is 12 inches in circumference, so it's a little less than 4 inches in diameter. So what's this shaft? 5 or 6 inches, I'm guessing. There's not a lot of through bore options for encoders out there that are greater than 2 inches. There's some rotary scales that get into the 500 millimeter range, but they're very expensive. They're not for something like this. They're for positioning rotary tables. So when you have a large motor output shaft or a large shaft on a gearbox that you're trying to get the speed of or the position of, a wheeled encoder is a great way to adapt a rotary encoder to run wheel against wheel to get that position. So here is the final product. We did a two-wheeled encoder against this large shaft to maintain a closed loop on the final output speed of that escalator. This is heavy equipment, a lot of encoders and heavy equipment. This is a buncher feller machine. You got a chainsaw at the bottom. Out in the woods of Alaska, this cuts down the tree, and then these grippers here grab the tree and they spin and they debark and delimit. Well, our little magnetic encoder here is installed in this wheel. So when the logging truck pulls up, they turn this sideways, and the operator actually just hits a footage, 8 foot, 10 foot, 12 foot. And once he hits that, this is all automated, and it's exactly the same length every time because they're measuring the linear distance of that log with an encoder inside this wheel. AGVs, major application now, probably one of our biggest growth areas for encoders. And it's a great example of draw wires, absolutes, and incrementals. You have a drive motor here, a traction motor running a caster wheel, and you want to know the speed. You have to maintain, typically redundantly with two encoders, you got to maintain the speed of this caster wheel. So we get our encoders to these applications all the time, incremental. You're not looking for a position. You just want to see those pulses to verify the velocity of the AGV. So that would be installed here. Right next to it, we have a steering axis motor. This rotates the caster. We need an angle. And for safety, we can't get that angle off pulses. We need that encoder to deliver the true angle. Power loss, skipped, whatever, every time. So we put an absolute encoder on the steering axis of this AGV to give an angle of where it's steering. And then take an absolute encoder and put it on one of our draw wires, or anybody's draw wire, and attach that to the forks. And this is becoming the most common way to measure the height of these forks. And that's not just on AGVs, that's on manual forklifts as well. There's a lot of push for safety in all industries. And now a lot of people have realized that, hey, we need to know the height of these forks even before we engage telescopes. If somebody has 2,000 pounds of load on these forks and they put these forks 4 feet up, this forklift, if it was manually operated, could still tip over. So even though it's still manually driven by a human, you will see encoders in these applications because it'll tie back to the governor and the control. The higher these forks, the slower the maximum speed of the forklift. Mobile equipment, again, this is very similar to a crane I'm working on right now. lot of CAN open in the mobile industry. CAN bus is pretty much it for any kind of mobile equipment. And this encoder is installed on the drive gear that turns the superstructure of this crane here. So there's a ring gear in here on the superstructure, and then we've got a drive gear that's running and it spins this crane. Well, now they need a position of this superstructure for the software that controls it. Can actually set pretty cool fake false walls, they call them. If crane operators working between two buildings in a city, he can actually set false walls that limit the movement of the crane to help prevent an accident of hitting the side of a building. And to do that, they need to know, the software needs to know the position of this superstructure. So there's an encoder now of ours installed to give that absolute position. Now that is on the drive gear. This ring gear is 180 something teeth, and this drive gear has, in the teens. So they use a multi-turn absolute encoder. They count the number of turns and the position, so they can take an encoder on the drive gear, but get a unique position for the whole run of the whole rotation of the major ring gear. There's also encoders on the spool to know amount of cable let out. And I've seen, we don't make these, but I've seen linear encoders built into the cylinders here for the length of the amount of cylinder that's been extended or withdrawn. Food processing. Considerations if anybody's in food, stainless steel, right? IP67, IP69K are big. We offer products with both those. A lot of manufacturers out there do now. I recommend shafted encoders wherever possible. This is an example of a shafted encoder. They weren't Slim Jims. Gosh, I forgot what kind of sausage was coming off this thing now. But this is spinning this shaft that's collecting product that lines up, and they're actually counting the product as it goes. So they're measuring the speed of this drum with this encoder, and it's hard mounted to this shaft. Now, I don't recommend through bore encoders with a hole in them, because if this were a through bore on a shaft, you would have an exposed seal right here protecting that encoder, and the shaft would be coming out. When you have a washed out environment, that's just a great way to get pressure. I don't care what the rating is, IP69 even, they can still fail when they get pressure up against them. So just better safe than sorry from that preventative maintenance question. Try and get an encoder that's got a covered rear end so that it's just totally enclosed. You can get what are called hollow bore encoders, which another way to say that is blind hole. There's not a hole all the way through. That's still a great way to couple on a shaft where the rear of the encoder is totally enclosed and not going to get sprayed on. Infrastructure. I like this example because it's, along with AGVs, safety is paramount in infrastructure. A lot of crane upgrades. This one here, I believe, is in New Jersey. The company's out of New York. And it's a lift bridge. And a lot of bridges that were built in the 40s and 50s need to get retrofitted. So this company does one at a time. They retrofit these bridges. They put new motors and controls in them, and they add feedback. They close the loop for safety. They also want to make sure that the bridge does not get cockeyed between the two towers and get jammed. So they have a motor on each side that lifts up the bridge on each tower here, and on each system they have our Model 260 encoder on running off that drive shaft. And as you can see, they have two. This is becoming more and more common. In fact, I'm doing a lot of custom applications to fit redundant feedback into specific areas in equipment, and it's for safety. So they're running two discs and two reed heads redundantly on this shaft. Reason being is that they always need to equal each other. If one of these encoders ever deviates more than a couple pulses from the other encoder, the whole system will e-stop and stop and go, all right, we have an encoder failure. And from a safety perspective, if you're on that AGV and you have an incremental encoder that's closing your loop for velocity, that encoder ever failed, you could have an AGV going crazy on the floor and driving into people. That can't happen. So you'll see a need out there for redundant feedback. That's two discs and two reed heads. Some companies sell them in a package. They'll still ready. You'll get a safety encoder. We don't do that because we find it's better to offer custom solutions where we get the two discs and two reed heads however you want them to a package you design. But they are out there off the shelf. If you need an off-the-shelf redundant encoder, you can get them. And this is essentially what they are. Two discs, two heads, totally redundant, in one basically soda can is what they look like. Oil exploration vehicle. This is a wheeled encoder running inside of a rim, and it's giving position. Driver drives it up to Canada. He falls asleep, puts it in auto mode, and it pounds the ground every 10 feet looking for oil. Our little wheel encoder has got a rugged job there, but how do you accomplish it? They're using GPS, that's one way, but they need a redundant way to verify that position, and they're running a wheeled encoder in the rim of the truck to corroborate the position with GPS on this vehicle. So it's a physical way to measure position. Another safety application here, this is out of Stagecraft. We've got a gearbox. This is a 90-degree gearbox here that has an encoder of its own in it, and it's running this big caster wheel here. So this big caster wheel runs up against a 40-foot diameter turntable on a Broadway stage. Well, there's human beings, there's actors and actresses on that table. What if that table jammed? What if a costume got stuck and jammed it and somebody's getting pulled into the table? They've added secondary feedback. So this is a wheeled encoder here that is not running up against this caster. It's being used as redundant or secondary feedback. It runs up against the table as well. So if that table does get jammed and all of a sudden the position of that table deviates versus what the encoder sees in the drive motor, this motor will stop versus running through and continuing to injure somebody getting pulled into the table. That's it. Any questions on applications?